Yeah. Enable பண்ணிருக்காங்க. சொல்லு. Those who are online, are you able to see the screen?
Yes, sir.
Sir.
So shall we get started? Yeah. So the next question is torque on a magnetic dipole in a magnetic field. right? So there is a magnetic field B that is existing, in which there is a magnetic dipole that is placed north, south, right? So basically a magnet only. I forgot to switch it. So I'll repeat it from the beginning for the recording. Okay. Listen to this. So the topic is going to be torque on a magnetic dipole in a magnetic field, for which we have magnetic field in which there is a magnetic dipole. That is basically a magnet that is placed, right? Now the question is, if the magnetic field lines are from left to right, what pole does the left side behave as? It behaves as a north pole, and this side it behaves as a south pole, right? Then what will happen? This north pole will start experiencing a force in which direction? It will experience a force in the rightward direction, and south pole will experience a force in the leftward direction, right? So if this force is F, this force will also be F, right? Basically, how much is that force going to be? Force experienced by the north pole will be equal to the pole strength of the north pole multiplied with the magnetic field. Similarly, force experienced by the south pole is going to be pole strength of the south pole multiplied with magnetic field. But they both are in opposite direction. So in terms of magnitude, they're same, and in terms of direction, they're opposite in such a way that they get nullified, right? But the system is still going to be in rotation. Why is it so? Because these two forces put together will create a couple. They act as a couple, so due to which the system is going to rotate. See, for example, if there is a magnet, if there is a force acting like this, and if there is a force acting like this simultaneously, both will make the system rotate like this. Am I clear? Right. So how much is the force it is going to experience? Let me call this distance as L, and let me call this distance as L. And let's say this is the axis of rotation. So what is going to be the perpendicular distance? If I take this to be theta, and if I take this, this will also be theta because they are vertically opposite. If this distance is L, this will be L sine theta here. If this distance is L, this will be L sine theta here. So force multiplied with perpendicular distance is going to be the torque. So torque experienced by the north pole is going to be equal to how much? Force into L sine theta. Torque experienced by the south pole will be equal to force into L sine theta, but both the torques are going to be in the same direction, right? Both the torques will be in the same direction because this force is also producing a clockwise rotation. This force is also producing a clockwise rotation. They are in the same direction. So net torque is going to be equal to F into 2L sine theta, right? But what is the value of F? F is QM into B. So QM into B into 2L sine theta. So QM into 2L is going to be equal to how much? QM into 2L is going to be equal to small m. That is a magnetic dipole moment. So small m into capital B into sine theta. See, this expression, we have already seen it in the previous chapter also. Right? Where did we see? For a galvanometer, before the concept of galvanometer. When you talk about the current carrying coil placed in magnetic field, it experiences torque of NIBA sine theta. So instead of NIA, we write it as M. So there also we learned it as MB sine theta. Here also it is MB sine theta, but the context is different. There it is a current carrying coil. Here it is a permanent magnet, but the mathematical expression is still the same. Clear? Just make a note of it. Let me know once you're done. Done? So the next concept is about the potential energy of a magnetic dipole in a magnetic field. Potential energy of a magnetic dipole in magnetic field. So in the same magnetic field, let's say you're placing this dipole. This is north pole, this is south pole. This is going to be the axis, and if I take this to be theta. Okay. So what is happening is this pole is experiencing a force in the rightward direction. This pole is experiencing a force in the leftward direction. Am I right? Now, there is a torque experienced by the system which is given by the expression mb sine theta, where theta is going to be the angle between magnetic dipole moment and the magnetic field. Let's say there is a torque which is creating an angular displacement of d theta. I repeat it. There is a torque that is creating an angular displacement of d theta, right? Then what is going to be the small amount of work done by the torque? Small amount of work done will be equal to tau d theta. So what is the value of tau? It is mb sine theta into d theta. Makes sense? So it is mb sine theta into d theta. This is going to be the value of dw. But what I want is the total work done. So for the total work done, I'm going to integrate it. Integrate what? Integrate mb sine theta d theta from an angle theta 1 to theta 2. So if I take that mb outside, then mb into, what is the integral of sine theta? It will be minus cos theta from where to where? Theta 1 to theta 2. So it will be minus mb into cos theta 2 minus cos theta 1. This will be the answer. Minus mb into cos theta 2 minus cos theta 1. Same. It's 0. It's 0. You know, these two forces are in opposite direction. On the situation, force was 0 only. Which one is inside? So I'm talking about the force experienced by the North Pole, force experienced by the South Pole. So the forces experienced by each pole are in opposite directions, but the net torque is in the same direction. Shall we proceed? The current loop as a magnetic dipole, I've already explained, that is a clock rule. When you take a current carrying loop, right? If the current is going to flow in the clockwise direction, it will act like a south pole. If the current is flowing in anti-clockwise, it will act like a north pole. Okay. So bar magnet as an equivalent solenoid. This is also in your syllabus, it is only qualitative analysis. Actually, there was a derivation, but that is removed. So you don't have a derivation. You need to understand the fact that a bar magnet is equivalent to a long solenoid. So what do I mean by that is, if you take a bar magnet, which is of north pole and the south pole, how is the magnetic field line going to be? It is going to be from the north pole to the south pole outside the magnet and south to north inside the magnet. Here also north to south outside and south to north inside, right? It keeps on going like this, right? Whereas when you take a solenoid, when you take a long solenoid, right? Now what will happen to this is, if the current is flowing in this direction, okay? If the current is flowing in such a way that it is going into the plane, let's assume that the current is going into the plane. Now, if it is like this, when you see from this side, right, how is it going to appear? The current is in this direction. When you see it from this side, it is in the anti-clockwise direction, right? If it is like this, it is in the anti-clockwise direction. So anti-clockwise currents will be acting as the north pole. So if one of the sides is north pole, the other side is going to be south pole. Because when the current is entering into the plane this side, on the other end, it will appear as if the current is coming out of the plane. So when the current is coming out of the plane this side, right, when it is going to come out of the plane, it will appear as if it is moving in the clockwise direction, because you are seeing from the same side. So when the current comes out of the plane, when you see from this side, when it is coming in this way, it will act like clockwise and a south pole. So what we are trying to tell here is, like the way the magnetic field due to a bar magnet along its axis is given as 2 times mu naught m divided by 4 pi r cube, the magnetic field due to a long solenoid along its axis will also take the same value of 2 times mu naught into m divided by 4 pi r cube. Okay, is the point clear? Right? Hence, what we are trying to say is that the bar magnet is equivalent to a solenoid. Okay, is the point clear? You can just make a note of it. See, for detailed derivation, if at all you are interested, I'll add it. I have done it. I'll add it in your app. Done? Done or not? Right. See, this chapter is divided into 3 parts actually. The first part is about these kind of introduction to magnetism. Second part is Earth's magnetism, and the third part is the magnetic properties of different substances. Okay. So if you see, this is the end of the first part. So here, Gauss law in magnetism is something like this. What is Gauss law in electrostatics? The surface integral of E vector dot ds vector is equal to the charge enclosed by the Gaussian surface divided by epsilon naught. Right? So when it comes to Gauss law in magnetism, it will be the similar kind of a format. The surface integral of B vector dot ds vector. So this should not be compared with Ampere circular law, because in Ampere circular law you have dl vector. That is line integral of B vector dot dl vector. Here it is a surface integral of B vector dot ds vector, which is the area, is given as, listen to this carefully, when I take the magnetic lines of force, that is a magnetic field lines, how are they going to be? They are always going to form a closed loop. So when they are forming a closed loop, what will happen is, wherever you consider the Gaussian surface, if I take a Gaussian surface like this, right, can I say that the number of field lines that are entering the Gaussian surface is equal to the number of field lines leaving the Gaussian surface? So to put it simple, the surface integral of E dot ds is nothing but flux. If you recollect it, this is the electric flux, if you recollect it, right? In a similar way, the surface integral of B dot ds is called as the magnetic flux. Okay. Now, when it comes to the Gauss law in electrostatics, if at all I have a surface like this, and let's say it is enclosed by an isolated positive charge, then what will happen is there will be only field lines that are leaving the surface. Suppose I have an isolated negative charge, then there is a possibility of the field lines entering the surface. So that is because it is in electrostatics, we can have isolated positive and negative charge. Whereas in magnetism, what happens is you will never have positive or negative, you will have both together. That is, you will always have a magnetic dipole inside in such a way that the number of field lines emitted by the North Pole will be equal to the number of field lines received by the South Pole. Means the number of field lines leaving the surface will be equal to the number of field lines entering the surface. If you take the field lines leaving the surface as positive, then the field lines entering the surface will be negative, right? Because I wrote phi1 and phi1 because phi1 is the number of field lines leaving the surface and phi1 is the number of field lines entering the surface also. But why did I put a minus sign? Because leaving I took it as positive, entering I took it as negative. So the total value is going to be 0. Meaning of it is, when you define the Gauss law for electrostatics, you can define it as the total flux is equal to the charge enclosed by epsilon naught. Whereas when you talk about Gauss law for magnetism, the total flux enclosed by the Gaussian surface is always a 0. This is what is the statement for Gauss law in magnetism. So this is the simplest statement. So just to conclude the story, right? The surface integral of B vector dot ds vector is always equal to 0. Why is it so? If somebody asks you the reason, why, what will you say? Suppose this comes as an assertion reason question. They'll give you this as a statement. And they'll give what is the reason they're supposed to give so that the reason is supporting the statement. No. It has no positive and negative charge. The number of field lines, the number of magnetic field lines leaving the Gaussian surface is equal to the number of field lines entering the Gaussian surface. Hence, the total flux put together will always be a 0. Is the point clear? Yes. Does anyone have textbook? I want to check if Earth's magnetism is there. This new book or old book? Newer. But I don't think Earth's magnetism is there. Did they teach you? No, I'm asking. No, or you don't remember. Earth's magnetism சொல்லி கொடுத்தாங்களா? Magnetic dip, magnetic inclination. அது மாதிரி எதுவும் சொல்லல. When I checked the syllabus, it was not there. Today is Wednesday or Tuesday? Wednesday. Wow. Okay. Let me check the syllabus once. So I'll tell you the topics. Listen to this. The syllabus. Bar magnet is there. Bar magnet has an equivalent solenoid, which is the qualitative analysis. So you don't need the derivation. Magnetic field intensity due to a bar magnet. Magnetic field intensity due to a bar magnet along its axis that we derived yesterday. 2 times mu naught m divided by 4 pi r cube. And perpendicular to its axis, for that they told qualitative treatment only. Okay. So it's not clear whether it is a qualitative treatment for both or is it only for perpendicular. Perpendicular means equatorial plane. Sorry, equatorial point. Okay. Torque on a magnetic dipole, which is a bar magnet which is placed in uniform magnetic field. The one which we saw today, and magnetic field lines. Magnetic field lines means you remember that compass which I drew and the tangent I told you. So that one. Actually, this is also not given, but I don't think there's a big concept for you to remember. All that you need to remember is the surface integral of B vector dot ds vector is equal to 0, and Earth's magnetism is not a part of your syllabus. So all that we need to understand is magnetic properties of materials, which are para, dia, ferro, magnetic substances with examples, and magnetization of materials, effect of temperature on magnetic properties. One class, that's it. Actually, it's simple. I told you, these chapters are small. So it's not there. Okay. So we need to start the second part of the chapter, that is understanding the magnetic properties of different substances. See, that one, what I'll do is I'll finish it in one class in the next session, because I didn't prepare some video visuals for it. Okay, I'll do it in the next class. But what I'll do is, since we don't have problems, in the previous chapter, I left one concept. The concept is called as velocity selector. I missed to explain it. Okay. So we can make a note of that point. So the heading is going to be motion of a charged particle in presence of electric and magnetic field, in which we are going to see one of the important cases, which is called as velocity selector. Okay. So it's called as velocity selector. Okay. Listen to this. Suppose you have electric field and magnetic field perpendicular to each other. So you have E vector and B vector perpendicular to each other, and you are going to project a charged particle. You're going to project a charged particle Q with velocity V perpendicular to both these fields. right? So what is happening? E vector and B vector are perpendicular. And what are you doing? You're projecting a charged particle Q with velocity V perpendicular to both these fields, right? But what is the objective of it? Simply, we don't want to project it. Why is the name called as velocity selector? Is because we need to project it in such a way, right? The charged particle should be projected perpendicular to both these fields in such a way that it does not experience any deviation. In the sense, if you project it in a particular direction, in both the fields, it should be traveling in the same direction. So let's try to understand what is the meaning of this. Okay. So for me to attain this kind of a situation, it does not experience any deviation means the meaning of the statement is that the net force experienced by the charged particle is supposed to be a 0. Net force experienced by a charged particle should be a 0. But the question is, net force means what is it going to be? It is going to be the electrostatic force and the magnetic force. So the electrostatic force and the magnetic force put together is supposed to be 0. Yes. So what should happen here is, listen, I'm going to do some understand. I'm going to do a small analysis. Let's say it's a positively charged particle. So when I say it has to be projected perpendicular to this, I can project it either in the direction of negative z-axis or positive z-axis. Am I right? I can project it in either direction of negative z-axis or positive z-axis, right? So what can I do? If I project it in the direction of negative z-axis, the charged particle due to the electric field will experience a force in which direction? Listen to this. If there is electric field like this, and you project a charged particle like this into the magnetic field, as soon as it enters, into the electric field, If there is an electric field and you project a charged particle Q into the electric field perpendicular to it, what is going to be the path taken by it? It will take the path in this way, which is parabolic in nature. A charged particle projected perpendicular to electric field will be a parabola. Okay. So in a similar way, if I want the charged particle, if I project the charged particle perpendicular to the perpendicular to the magnetic field, what will happen to it? It will move in a circular path. Right. The question is, what is the force that is going to experience here? It will be Q into E vector. What is the force it is going to experience here? It will be Q into V vector cross B vector. But what am I expecting in this case to happen? QE should be equal to Q into V vector cross B vector. Right. So using the same logic, tell me, if the electric field is like this, when you project the particle in this direction, what path is it going to move? It is going to move in a parabolic path. And due to the magnetic field, it is going to move in a circular path. Am I clear till that point? Right. So if I write the net force as F vector, then F vector according to Coulomb's law is according to Lorentz force is supposed to be Q into E vector plus B vector cross B vector. Am I right? So if this force is supposed to be equal to 0, can I conclude that Q into E vector should be equal to negative of Q into V vector cross B vector? But in terms of magnitude, what are they supposed to be? They're supposed to be equal. So QE should be equal to QVB. I directly wrote it as QVB because V and B are perpendicular to each other. I told you, velocity of the particle is perpendicular to the magnetic field. So this QVB. So Q and Q will get cancelled so that you have V is equal to E divided by B. So whenever you have a situation where the electric field and magnetic field are perpendicular to each other and you project a charged particle also perpendicular to it, then the charged particle will travel undeviated. That is, it will not experience any net force on it. What scenario? When you project it with a velocity v is equal to e by b, and that velocity v is what is called as the velocity selector. Is that point clear? Just make a note of it. You done? So let me know if you're done. You're done writing? Okay. See, since we have time, I'll just show you a video. So listen. Those who are online are able to see the screen?
Yes, sir.
Yes, sir.
Oh, listen. So since I told you, there is some activity-based thing where you can see whether the materials are ferromagnetic. I'm just giving you an introduction to the next part of this chapter, that is the magnetic properties of substances. Based on the magnetic properties, we are going to discuss about three important substances which are called as para, dia, and ferromagnetic substances. This is just a video for you to understand how each substance is going to behave. I'm not sure why you're not able to. So listen, I'll come from the beginning. So three types of magnetism, which is going to be. So observe. Did you observe what happened to the water? Like what happened? When you took the pole, when you took a magnet closer to it, it started moving away, or it did it get attracted or repel? It was repelling. This is a either parrot or diamond.
different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron.
See, this I have already shown you. If you remember on the other day, I took the bell pins, right? I connected it to, I just magnetized the bell pins with the help of a small bar magnet. And with the help of the first bell pin, I was trying to hold the second. And after some time, you would have seen that the bell pins were attached to each other, right? Why did that happen? Because the bell pins attained magnetism and they were retained. So most important thing is wherever substances are going to retain this magnetism are going to be like for a longer duration are going to be ferromagnetic substances. If you remember in galvanometer also we discussed about one thing. What is the core made up of? I told you at that point. It is some iron core. It's called soft iron core. If you recollect it. So why do we use a soft iron core? Because we don't want that material to retain magnetism. Okay. So iron itself it's a ferromagnetic substance. In ferromagnetic itself, there are again two types, soft iron and the hard iron. Soft iron does not have the greater retention. So it will lose its magnetism faster, whereas the other one will have for a longer duration. So in one such category, we have this ferromagnetism. Is going to do the same activity with a different magnet and different substances. Observe.
Becomes a magnet in the presence of the magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary.
So, did you understand what is ferromagnetism? You take iron particles, and those iron particles getting attracted by magnets, right? We call it as those iron particles have ferromagnetism. They are ferromagnets. Now the question is, what is a paramagnet? Paramagnet is also similar to ferromagnet in the sense they will also get attracted to the magnets, but they will not be as strong as that of a ferromagnetic substance, right? So observe what are all the paramagnetic substances. So he's going to take this material to different substances. You have the names written there. No, observe what is going to happen. Is it getting attracted or repelled? Attracted. Now you're able to understand what the torque is. Liquid oxygen.
Which sticks to the magnet. I'll explain why later. Cadmium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the
So did you understand what happens? Paramagnetic substances will actually get attracted to the magnets, but they will be feeble. Whereas ferromagnetic substances get attracted at a rapid rate and the attraction is going to be stronger. Right. Now the next question that we need to understand is the counterpart of it. What is a diamagnetic substance? So basically diamagnet is opposite to paramagnet. Paramagnet gets attracted. Diamagnets will repel. So one such example that you saw already. Water is an example of diamagnetic substance, right?
opposite of paramagnet. They are always repulsed. They would rather die than be magnetic. An important example of this diamagnetic material is graphite. This specially made pyrolytic graphite is diamagnetic field. Don't be confused. This is not static electricity for edicators. Graphite is repelled by a magnet, always, both by the north and south. Pyrolytic graphite is a grown crystal of black carbon layers, which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite.
You know what that phenomenon is called as? There are trains also being designed on this. Maglev. You have heard of this word maglev? Basically, it is a short form of magnetic levitation. So levitation means something is hanging in the air. It is getting suspended in the air. It is neither flying away nor coming down. It is exactly balanced in the air. And why is it happening? It is because of the diamagnetic property of the superconductor. So what do we call this as? Magnetic levitation, or in simple terms, you call it as maglev. So first three letters of magnetic, first three letters of levitation, maglev.
Most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth powered boat sails toward the bigger magnetic fields. One way to check whether an object is diamagnetic or paramagnetic.
See, I'll just tell you one thing. Whatever I'm showing you here is a complete thing that we are going to discuss. This one video is enough for you to complete the second part. The only thing that I didn't prepare is the table. So what I'll do is from whatever we have seen here, I'll just tell you how the table works. That will be done in 20 minutes. Okay, so concentrate. I hope you're able to visualize it, no? Now you know what is a paramagnetic substance, what is a diamagnetic, and what is a ferromagnetic substance. So ferromagnetic and paramagnetic substances get attracted to the magnets, whereas diamagnetic substances repel. Okay. Now, if you take this North Pole and South Pole, if you suspend, let's say this is a paramagnetic substance. If you take a paramagnetic substance and suspend it, you remember the other day I was suspending the magnet, no? Instead of magnet, let's say you are suspending an aluminum coil. Now, what will happen is when you suspend it perpendicular to this, it will slowly start aligning itself along the magnetic field. If it is a paramagnetic substance. If it is a diamagnetic substance, what will happen is it will try to align itself perpendicular to the magnetic field because it does not want to take the magnetic field. It always wants to repel the magnetic field. So where is the magnetic field less? Along the perpendicular, and where is the magnetic field strong? Along the axis. Okay. So see what is going to happen is. So glass is a diamagnetic object. See how it will align itself. It is trying to align itself perpendicularly. Okay. Now, what we need to answer is why is this behavior even coming into picture? Right. So if you, of course, try to understand why these properties are coming, it is coming because of the chemical properties of it. Right. So when you talk about the, when you go back to the atomic structure and see the number of paired electrons that you have and the unpaired electrons you have, that will decide whether the substance is a paramagnetic or a diamagnetic. Ferromagnetic, it is understood, it is a family of iron. Whereas paramagnetic and diamagnetic can come from anywhere. If you take aluminum, for example, how many valence electrons do you have? Aluminum. What is the atomic number of aluminum? So 13 means how much do you have? 2, 8. So 2 in the first, 8 in the second, and 3 in the third. So in those 3 electrons that you have, 2 will be paired and 1 will be unpaired. So paramagnetism is exhibited due to that unpaired electron. Whereas when you take a diamagnetic substance, for example, water is an example of diamagnetic substance. When you draw the structure of water, hydrogen, hydrogen, and in middle you will have oxygen. Oxygen contains how many lone pairs? See, oxygen has, see, 6 electrons. Out of the 6 electrons, 1 electron is shared with 1 hydrogen. The second electron is shared with the second hydrogen. So 4 electrons are left out. 4 electrons divided by 2 will give you the number of lone pairs. So 2 lone pairs it has. So does it, lone pair means they are paired. Name itself is suggesting they are paired. Means water does not have any unpaired electron. So substances which do not have unpaired electrons exhibit the property of diamagnetism. Is my point clear? Did you understand what I told? So substances which have unpaired electrons in the valence shell will be paramagnetic. Substances which have paired electrons will be diamagnetic. So that's what, or that's how the table is going to help. Actually, in your chemistry, just sorry to disturb, but yeah, in your chemistry, you had a chapter called solid state. It is deleted actually. In the solid state, you will be seeing all these things. The introduction would have been given there. Okay. Paramagnetic.
That's 2 and 1 p.
So what hybridization is this? Did you understand that unpaired electron is the one which is making it a paramagnetic substance? Yeah, same example.
Has at least one unpaired electron.
That's it. Actually, this is the whole chapter itself. யார் இவன் யாருன்னு எனக்கு தெரியாது. Okay. Okay. 1 minute. So if you see, the whole context is already covered. Based on whatever you saw in the experiment, what we are going to study is, I'll put a table like this. In the table, you have paramagnetic, diamagnetic, ferromagnetic. How those substances are going to respond to different external magnetic fields. That's what we are going to see. And there are some terms that you need to see. One is called as magnetization, then there is something called as intensity. All those things I'll explain it in the next class. So maximum half an hour to 45 minutes we'll be done with this. Is that clear? So again, I will not show this video. If you want, you can share it in the group. You can have a look at it. Right? So is everything clear? Shall we wind up? So those
Yes,
who are
sir.
online clear?
Yes, sir.
Yeah.
Thank you, sir.
Yeah, thank you. See you guys.
Thank you, sir.
Yeah, ma'am.